Rotary Position Embeddings, or ROPE for short. Essentially what it is, it's a way to embed or encode information about the positions of the tokens that a transformer needs to really understand sequence. For example, let's say here we take an image. This could be applied to text, to audio, whatever. In this case, let's take an image, we chop it up into pieces. Every one of these pieces is a token. The A, B, C, D tokens are fed in parallel at the same time. Because they're fed in parallel, they're no longer sequential. So the transformer needs to know the positioning, the order of the tokens. Which one comes first? Is B position 2 or is it position 3? We need to be explicit about this information. How far is C from token A? How far is token D from token A? This is what we mean by positional information. At the beginning, they started with absolute position information, which is basically a fixed vector like here. So let's say this one, a fixed vector that initially they used the sinusoidal formula to come up with that, and based on the frequency of the sine function, it would determine the position of the token. So the vector here in blue is the embedding vector. This is the actual meaning of the token, right? Here in blue, we would transform that blue vector by adding the position information, and that would be the input to the transformer. So this would happen before the transformer kicks in, like we see here. So this is the input of the transformer. We're actually getting the embeddings, and we're adding the position encoding to the token embedding, and then we're feeding all of that in. Okay, so instead of taking our token vector and transforming this token vector by adding a new vector, here is where rope comes in. We're actually gonna transform this vector, the token, by rotating it. So we're gonna rotate the token embedding based, like the angle of rotation is gonna be based on how far it is in the sequence. So let's take the vector dog. Okay, let's say this is the position in space. If dog is in token number 2, we're actually going to rotate it. We're actually going to rotate it by theta. If it's deeper in the sequence, we're actually going to rotate it by another theta. So the rotation will encode where it is in the sequence. So we established the fact that we're going to encode the information about the position of the tokens through a rotation. Now, rotating in Euclidean space is actually not very efficient because rotating by a rotating matrix in high dimension is actually very complicated and cumbersome to do. We also have the fact that we're actually limited with how much we can fit in there. So you can have collapse of the vector. We can rotate one vector onto another by accident, and so the meaning would be confused. The meaning of one token would be confused with the meaning of another token that has been rotated based on its position. So you can have collapse of vectors. These vectors are all already pointed in different direction in this multi-high dimensional space. So as you rotate things, it becomes difficult to actually interpret the geometry of those. Here is a summary of the problems in 2D. So aside from the fact that it's really cumbersome and complicated to actually rotate in high dimension in your Euclidean space, and also the fact that you can rotate another vector onto another because things are more finite in your Euclidean space, it actually doesn't capture the relative positions between the tokens, which is super important. You really want to know how far one token is from the other, and you want to encode that more precisely. And currently, with the absolute position, you can't really know the difference between token 1 and token token 4 as opposed to token 1 and token 100, let's just say, that difference is not proportional. The other thing is it doesn't really generalize well beyond the max length of the transformer sequence. So let's assume it's 512. You can generalize, you can learn the positions below 512s, but anything above that, it doesn't generalize well. The other thing is sinusoidal positional embeddings, which is what is used for absolute at the beginning. At least they have very weak extrapolation, so they actually cannot extrapolate to positions that are further away. And we also have the geometric interpretation. We need the model to reason about the distances between the tokens. So let's say you have two tokens. You have apple and banana. As long as token apple and token banana are 3 tokens apart, whether it's at position 3 and 6 or position 303 and 306, you'll always have the same attention score for those two. So Euclidean space is actually not very good for us right now. We need another space, okay, that actually has those properties. So this is the complex space. So the complex space, what's nice about it is that as we rotate, you can change the angle, and while keeping the magnitude of the vector preserved. So that change of angle, it actually contains that information, not just for the absolute, but between the tokens themselves, which is limited in the Euclidean space. There's also the issue with collapsing is not really there, because every complex number, it has a unique polar representation. So each vector remains distinct, and that's very crucial for us. And the complex plane, because there's an imaginary component, is very smooth, very continuous. So vectors are not going to collapse one into another. So we cannot use 2D because of all of these problems. We need another space. So complex space is great. It has all of the properties that we need so that things are smooth. We can have as many unique, distinct vectors that we can rotate all over the place, and all of the geometric interpretation is there. So how do we get to that complex space? We need complex numbers. That's where the special formula of Euler comes into play. When we rotate a vector, we're actually going to rotate it by e to the ix. Okay, this will help us to move to the complex imaginary space. E to the ix is equal to cosine of x plus I to the sine of x. That's the famous formula of Euler. There's another way to interpret it using 2D matrices, which is the one right here. So you have cosine of x minus sine of x, and a cosine of x. So we're going to be multiplying our vectors by this matrix right here. So how will this work in more details? So we're going to take the token of the embedding. We're going to multiply it by this query matrix. This is how token embeddings are being learned. And then we're going to multiply it by this e to the im theta to actually embed the position information. So this is going to be at the beginning of the learning process, so that we set things up. Okay, and as we said, the theta, we're going to rotate the query, the key vector, by a certain angle that is proportional to the position of token m. We're going to do the same thing for the key. So we're going to take our key embedding. We're going to multiply by our key matrix. So we're going to be learning our token embedding, and then we're going to multiply it by our ein to the theta, because the theta depends on the position of the token. That's at the beginning once we set things up. It's not just important to have the initial position, because as we're learning, this information is going to be diluted. We always need to keep into account the relative difference between the token. So as we're going to learn in our self-attention, we're going to take our token m multiplied by our matrix Q. We're going to take our token n multiplied by our key matrix, and then we're going to rotate the product of these two by an angle that's actually proportional to the difference of m minus n. That's where your relative distance comes into play. And the final result of the attention is actually just the real part of that. So because your complex space has a real and imaginary component, we're actually gonna review this as the real part of it, and that's going to be fed into the attention. So we want our attention to actually not only do this part, but we're actually going to rotate it by an angle that's actually the difference between token M and token N. We're going to dive a bit deeper just to illustrate that example. Let's just say we have a two-dimensional vector. Okay, we have this vector right here. So if we plot this vector, which is this one, okay, this is x1, x2. As mentioned, the whole point of rope is to rotate a vector in a 2D space, and that rotation encodes the positional information, okay? And we're in a 2D space. As we are rotating it by theta 1, we're going to get this new vector, okay? And that's our new vector that's rotated, and that the magnitude is preserved, so your information is maintained, but the direction, where it's pointing to changes, and that change of orientation has that positional information. Now, language is very complicated. In reality, this happens in a multidimensional space. Now, rope doesn't rotate this vector the same way in a multidimensional space because things are more complicated. So if you rotate the vector as a whole across all of the dimensions in one shot, you actually lose the ability to capture all of the complexity and the nuances of the language. So what rope does, it actually takes every pair of the embedding and rotates that separately. And it actually rotates it based on where it is in the embedding. So if we just look at this example, let's say we have the word enhanced, and this enhanced has some sort of a certain length of token embedding. So it's going to break it up. Every two is going to be a chunk. And this one is going to be another chunk. And so we're going to take this chunk. So this is pair 1. This is pair 2. Okay, so let's say we just take pair 1 right here. Okay. What's going to happen is that the first element of this pair is going to be the real component. The second element of this pair is going to be the imaginary component. And we're going to rotate that one by itself. And that one is going to give us a new x1, x2 prime. Then we're going to move on to the second pair, okay, right here. And then we're going to do the same sorts of rotation. And we're going to end up with a new embedding right here. When we rotate the vector by theta, how are we actually going to know the theta to rotate by? So to answer that, let me just back up a bit because we spoke about a lot of things. Let me just review some of the stuff here. So in rope, there are thetas that we pre-compute for every token. This is what we do here. Okay. So there's a lot of thetas that we need to pre-compute. How do you know how to come up with all of these thetas? So let me just write up a small example. So let's say I have a sentence, I love pizza. Okay. And every one of those, so that's 3 tokens, let's just say. Every one of those tokens, it has an embedding. Okay. And in the embedding, so I'm going to do all of these slices. Okay, so let me change the color here. So this is position 1, This is position 2, this is position 3. We've spoken about how rope, we don't rotate the entire vector in one shot. We actually take every 2 consecutive dimension and we pair it as 1. So this is pair 1. This is pair 2. This is pair 3, and so on and so forth. So the thetas that we pre-compute, we need to compute as many thetas as we have combinations of tokens, token position, and pairs, right? So we have for I and this one, we have theta 1, 1, 1, let's just say. For I and the second pair, we have another theta. For I and the third pair, we have another one. I'm just going to reduce this slightly. Okay, and same thing for this one. Here we have theta 2, because this is for position 2, pair 1. Theta 2, position 2. You get the idea. So we need as many thetas as we have tokens in the sequence and pairs in the dimension of the embedding. Let's go a bit in the code here. So you can think of this sequence as it has m positions, and think of this sequence as thetas, where every theta is for a pair. So actually we're going to need m times theta combinations. If we look here at this one, when we actually combine all of those m and thetas, you're going to get a matrix like this one here, right here. Okay, small recap. The Euler's formula, it's e to the ix. It's we mentioned it's, you can interpret it as this 2D matrix right here, right? And so this is what every one of those is. So the thetas are going to be created based on this formula right here. Okay, so it's 10,000 to the minus 2 I minus 1 divided by d. I, where once again I represent at which pair are you looking at in that sequence. So let's look at some code. So this is the code to actually pre-compute those theta positions. So the first thing is that we need to create a series. Okay, we're going to create a series from 0 to the dimension of the vector by 2. So it's going to skip every 2, because we said here that we're only taking a pair at a time, right? We are rotating every pair at a time. So we create a series for that, like a sequence. And then to create the theta, you apply this formula. So the formula is actually, so it's 10,000 to the minus 2 I minus 1 over d. This would be the same thing as 1 over 10,000 to I minus 1 divided by d. And so this is what's doing here. It's 10,000 to the theta numerator divided by the head dimension right here. You're getting all of your m's, which is the sequence length. So m is the length of the sequence. This is what we wrote right here. So in this case, it will be 3 in this simple example. And then what we want to do is that we want to get all of the combinations of m, right, with all of the pairs here. So that combination is done using the torch.outer function. So that's going to give us the rotation angle for every position and dimension combination. Once we have that, then we need to actually convert it to polar system, or to bring it to the complex space. That's done with the torch.polar, which effectively what it's going to do is it's going to take like m1 theta 1 is going to convert it to cosine m1 theta 1 plus I sine m1 theta 1. That's basically what we spoke around here. That's Euler's famous formula. So that is the block of code that is executed at the beginning to get all of those initial theta values that are going to be used later on. So now that we've actually pre-computed the thetas, we have what we need to actually rotate the vector. So how do we come up with actually how to rotate the vectors? Let's go back to our example right here. So let's say we're taking the first two consecutive dimensions, x1 and x2. Right, so it's like right here. We're going to take the first one, that's the real. We're going to take the second one, that's your imaginary. And so we're going to convert this x1, x2 to a complex number by taking x1 as the real, x2 as the imaginary. We're going to multiply it by what we've pre-computed. So if we just go back here to the code, we got our, change that. We got our m1 theta 1. It got transformed to polar coordinates as so. That's your pre-computed for specifically for the first the token at the first position for the first pair. We're going to use that. We're going to plug that right here, and we're going to multiply. Pretty simple. As we multiply, after all the math, we're going to get something like this. Okay, that's your 2D rotation matrix in complex space. So this 2D matrix, which only focuses on the first two dimensions of the entire token embedding, is actually the same as this one. Okay. So basically, this whole matrix is for different theta pairs, but for the same token position. So in other words, this is equivalent to your x times your r m to the theta. As for the code, what we did here, this whole multiplication, this whole plucking the first like one pair out, making it into a complex, multiplying by the pre-computed. This is all found in this code block right here. So here we are taking we're taking the x here, we are reshaping it and taking two consecutive dimensions and we're grouping them. This is what this line does right here. We are adding a batch and head dimension at this line, and we're actually doing the multiplication of the complex with the pre-computed, which is this one. We are taking the real component of the result, we are reshaping it, and then we are returning the rotation matrix, which would be this guy right here. And ultimately, this would enable us to actually rotate the token embedding. I hope this was useful to you, and good studying.